Okay, so in this video we're going to work specifically with inverse Laplace transforms. To jog your memory, we have a differential equation of an independent variable t or x. Now for us t will be time and x would be distance along a beam. And solving this can be a hard problem. So what the Laplace transform does as such, one way of thinking about it is it turns it into an easy problem and a medium hard problem. So the Laplace transform translates the differential equation into an algebraic equation, and then this algebraic equation, this is easy to solve. And then the medium bit is sending this back. Now in the background we have a table of Laplace transforms which are at the back of your manual. Okay. Now the first thing to look at here is that this thing may not be in the tables. We need to write it as a sum of simple things, and this is what doing partial fractions is. And we're a bit messy here. So we're just looking down the bottom of this page. So this is the example we were looking at the last day. And if we look in the big tables, this isn't here. So what we have to do is we have to write this as a sum of simple terms, and this is doing partial fractions. Now the first step with partial fractions is to factorize the bottom, but unfortunately this wasn't possible in this sense, and also the b squared minus 4ac was negative, and this means that this has no real roots, and if it has no real roots it has no real factors. So this was a bad problem that we faced the last time we were in class. So this was all done the last day in class. So what we were able to do was we said we would what's called complete the square. And we did this the last day, and where we are now at this stage is here. Okay. So we'll talk again in a later video about why did we do this. Okay. So we don't know exactly what to do here. So one tempting thing to do is to split it up as 2s divided by this plus 1 divided by this, and then you can take the 2 out. But you've got a little problem here in that you're looking for something like s over s squared plus 2 squared, but unfortunately this top s has not been shifted. This term is fine, but this one is not. What we want is to get a shifted cosine looking something like this. So this is this plus 3 and this plus 3. So this is what you'd call a shifted cos 2t. If you have s over s squared plus 2 squared, that's cos 2t, but because both the s's are shifted, it's a shifted cos 2t. And this isn't what we have up here, where the s on top isn't shifted. So this, now we have said this is the most difficult question we'll see in this module. So what you actually have to do is take the 2 out in the first instance. So do that straight away. Now what are you left with then? Now if you take the 2 out of the 1, it has to be equal to a half. This is something that it's easy to see from here, because if you do 2 by s, you get to 2s, the 2 by a half, you get 1. So when you're taking out the 2, you have to say, okay, 2 out of 2s is no problem, that gives me s, but 2 by what gives me 1, and it's equal to a half. Now then this next bit isn't easy either. So what we're trying to do is we're trying to get s plus 3 on top, and we've got s plus a half. So what you do is you write down what you want to happen, which basically means you write down the plus 3. Now that will change the top, and to make it the same you have to do minus 3 as well. So this bit in the middle, this is like adding 0, which is no problem. Then this is just explicitly showing that the half minus 3 is minus 2.5, and now we split it up. So you have the 2, now both of them are multiplied by 2. There's possibly an additional line that I could throw in here, which would be 2 times, I could have put a bracket, s plus 3 divided by s plus 3 squared plus 2 squared minus 5 over 2, and then the same quadratic on the bottom, s plus 3 squared plus 2 squared. Okay. So then you need to multiply this out. So you'll 2 by the first thing and 2 by the minus 5 over 2. So that's where this next line is coming from. Now the first term is great because it's exactly like this thing up here, in that it's an s over s squared plus 2 squared, which is in the tables. It is a shifted one. We'll go back talking about that in a second. Now the second one as it sits isn't great because what you're comparing, and it's on this previous page, or maybe backwards. Okay, so I just want to pause. I don't know if that freezing works, but anyway. Well, anyway, on we go. So maybe at this point it's good writing down something that might have been written somewhere else, but doesn't seem to have been done. So when we're looking at this, the original thing really, what we were hoping was that maybe, so the original thing which was called f of s, so you'd have to go back to page 119. It's basically this thing here. That maybe it kind of looks a little bit like s over s squared plus omega squared. This is a cos omega t when you send it back. And it also looks a little bit like omega divided by s squared plus omega squared. And that's a sine. So what we're trying to do here is write this as a sum of these. So the bottom we've kind of set up with the s plus 3 is that the s has been shifted, but we need to match it. So this here needs to be s plus 3 on top as well. They both need to be shifted. Now the issue over here is because we've got the 2 here, this means that certainly omega is equal to 2. And what we need is an omega on top as well. We need a 2 on top as well. Now there's different ways to approach this. Like essentially what's done here is I've swapped the 2 multiplied by 5 over 2 for 5 over 2 multiplied by 2. And of course order of multiplication doesn't matter. So that is actually fair enough. The other way of thinking about it is you could take out, well, there's different ways, but you could take out the common factor of 5 over 2. So you'd have 2 by 5 over 2. And then you could put the 2 there. And then you also divide by 2 out here. So it'd be multiply by 2, divide by 2. And then this 2 divided by this 2 would be 1, and you'd have this. Okay. Now this is actually, all the manipulations have been done. This is ready to be sent back. So what we're going to say is that we're going to recognize this as shifted. So this is a shifted version of this. Well, twice a shifted version of that, and the omega is equal to 2. And this is also a shifted thing. Now, I wouldn't necessarily write this down, but this is kind of saying what it is. Okay, here's the 2. And this is the Laplace transform of something where the s is shifted to s plus 3. And then you've got the minus 5 over 2, and this is the Laplace transform of something. It's like omega over s squared plus omega squared. But again, the s is shifted, so we'll just highlight all the shifting. Now, what we then have is the first shift theorem, which is in the tables. It says if you're bringing back something that is shifted, bring it back as normal, and then multiply by what's called an exponential shift. So I'll try and write this down and see how we get on. So we're sending this thing back. This is big F of s. It's been manipulated. So it'll send back to little f of t. Okay, so we bring it back linearly, which means you do it term by term, fixing constants. So we'll fix this 2. And then, as we said, okay, so this is a shifted cos 2t. So bring it back as normal. If it's shifted, bring it back as normal, as if those 3's weren't there. It would be one of these, s over s squared plus 2 squared, and this is a cos 2t. So bring it back to the cos 2t, and then we must multiply by the exponential shift. So here the shifting was s to s plus a, or rather s to s plus 3. So the a is 3, so we multiply by e to the minus 3t. So this is how you bring back a shifted cos 2t. Now we must bring this term back, minus 5 over 2. and this is a shifted sine 2t. So bring it back as normal, and then multiply it by the exponential shift, and of course the shifting here is the same, s to s plus 3, so the a is 3, so it's e to the minus 3t. Now what I would invite you to do now is to pause the video, well, just before you pause the video. So I'm going to ask a question, and after I ask the question you should pause the video. So the question is, what type of damping is this? So I'm going to pause the video now. So now you're back. Hopefully you have thought about it, and the answer is that it is, well, let's think it out. So let's say you couldn't figure it out. How, like, I don't want to just say the answer. So you got time, and this is, in this context, a displacement. And what you have is a wave. Now, if you add waves together, you get a wave. So you got a wave multiplied by exponential decay. So the blue bits want to essentially do this, but they're multiplied by something getting smaller. So you got a wave that's getting smaller and smaller in amplitude. So something like, perhaps, now we'll see the graph of it on the next page. Maybe it doesn't look like this, but this is underdamped. So in terms of a door closer, it should have been slowed down, but it doesn't. It ends up, if there's a door frame, it'll slam, otherwise it'll oscillate. So this is underdamped. I'll just write under. And this is the hardest question we'll see here. So if this is difficult, don't feel too bad. You can watch this again. If you can master this, no fear of you. So here it is. Now this one, I don't know why exactly, but it is underdamped because you see it slamming. It's not terribly underdamped. If it was really badly underdamped, it would actually keep swinging back and forth. Okay, right. Now we'll do these examples as well. Now the takeaway from these is that when you see the question, you don't really know if it's going to be easy or difficult. So like there doesn't seem to be a whole pile between these. So basically it means you can't say, oh, this is this type of question, I'll do it like this. That is that type of question, I'll do it slightly different. You have to just approach it as it is. Okay. So I'm looking at this, and what am I thinking? I want to send it back. I want to look in the tables. Now the tables all the time, by the way, are at the back of your manual. I can't write them here, but you can maybe have them in front of you or whatever. So it's not in the table. So what I want to do with this ideally is write this as a sum of simple things, because we're always good with sums. Because the Laplace transform and its inverse are linear, we can send things back term by term, fixing constants. This is the same for this. We want to also write this, but I suppose we'll get to that a little bit later. And doing this is called partial fractions. You shouldn't necessarily think straight away of partial fractions. There's a lot of questions we'll see later that when you're ready to send it back, it's already in the form, there's nothing to do. Okay, so the first thing to do with partial fractions is factorize the bottom. So we're talking s squared plus 4s, plus 3. So I'm going to use my AC method. I multiply a, which is 1, by c, which is 3, and I get 3. And I look at all the factors of that, I get 1 by 3. And can I write plus 4s as a sum of those? The answer is yes. I can do plus 1s plus 3s. Sorry about the seat. I probably have to... Anyway, okay, so s squared. So the 4s I can write as s, or 1s even, plus 3s plus 3. And now I can take out the common factor here. I get s times s plus 1. And then I plus take out a common factor here of 3, s plus 3. So just about space for s plus 1 times s plus 3. And that's great because I've got 2 rule 1s. And when I have 2 rule 1s, I can do the cover-up method. So the cover-up method says, okay, you have this 6s divided by, now don't put in s squared plus 4s plus 3, put in the factorization, s plus 1 times s plus 3. Now the cover-up method says, well, not the cover-up method, partial fraction says rule 1 will be, it'll be some constant over s plus 1, and it'll be some constant over s plus 3. And we can find these constants pretty much straight away using this cover-up method. So the cover-up method says when you want to find the constant for s plus 1, what you need to do is think what value of s makes s plus 1 equal to 0. Pause if you want to have a think. So the answer is minus 1. So you cover this up and you put minus 1 into everything that's left. So you'll have 6 times minus 1 over minus 1 plus 3. Similar story for the s plus 3. You say, okay, for what value of s is s plus 3 equal to 0? The answer is minus 3. So you cover it up here. And put minus 3 into everything that's left. So you get 6 times minus 3 over minus 3 plus 1. And hopefully we can simplify these. So the first one is minus 6 over 2, which is minus 3. And the second one looks like minus 18 divided by minus 2, which is plus 9. And these are in the tables. These can be sent back term by term, fixing constants. The constants here are the minus 3 and the 9. So sending it back, happy days, f of t. Look in the tables for 1 over s plus 1. It's 1 over s plus a. Goes back to e to the minus at. In this case, e to the minus 1t. So fix the minus 3, e to the minus 1t. Plus fix the 9, e to the minus 3t. What type of damping is this? Well, you've got two different speeds, so it closes fast and then slow, and that means the damping is too strong. It is over-damped. Now, not every differential equation is a door closer, by the way, but there's no harm. These two are actually, as it happens. Okay. Now we have to understand we're still just doing the fourth step of 4. We haven't actually done any exam questions yet, but we've already seen the most difficult. Okay, so that was not too bad, and indeed the first 3 steps of that question are actually not too bad. So what we need to do now is go at this yoke. Same as before, it's not in the tables. We want to write it as a sum of simple things that is in the tables. The first step is to factorize the denominator, factorize the bottom. So I look at s squared plus 4s plus 13. I do the AC method, 1a by c, 1 by 13 is 13. I look at all the factors of 13, but unfortunately the only factors of 13, because it's a prime number, are 1 and itself, and I cannot make up 4. Now that's bad. That is genuinely bad, but it's not necessarily the end of the world, because we know if we can find the roots of this, we can get a factor. So for example, technically you could do the minus b formula on this, and you'd get roots minus 1 and minus 3, and the factor theorem says s minus minus 1 and s minus minus 3, in other words s plus 1 and s plus 3 will be factors. Now I don't recommend that you use the minus b formula to factorize, but technically you could. And we definitely want to do it here because this method of factorizing didn't work. So you look at the minus b formula. Now you don't jump straight into the minus b formula, especially in an exam setting where if you can't factorize it, the odds are it has no real roots. Just look at the thing inside the square root. So just look at the b squared minus 4ac. And in this case, the b is 4, so you have 4 squared minus 4, a is 1, and c is 13. And this is 16 minus 52. It's certainly negative. And what that means is You've got a square root of a negative number. That's not a real number. So the roots are not real. So then the thinking is no real roots, which implies no real factors. And this is bad. Now I just need to think about space for a second, because I want to explain the thinking now. Where is this completing the square coming from? So I'm just going to grab, and I suppose I can do this the whole time, I'm just going to grab a spare piece of paper here, and I'm going to say, okay, how the hell do I know to do this? Okay, so the bottom of g of s does not factor, and so I'm left with 4s plus 8 over s squared plus 4s plus 13. And the only thing I have to send back is the tables. Now if I look in my Laplace tables, what do I see? I see in the t domain, I see in the s domain. And the two things that look possibly like this are sine and cos. So cos is s over s squared plus omega squared. That's sine omega t. And cos is omega over s squared plus omega squared. And this is, as we said, cos omega t. Now, it's not, the 4s is messing this up, but there's a possibility that this is like shifted sines and shifted cosines. So we also have our first shift theorem that says if you have something like this, but with the s shifted, say for example to plus a, that you can do this, you send it back as normal to f of t, and then the plus a shifting over here gets multiplied by what we call an exponential shift. So the hope would be that this looks a little bit like this and a little bit like this. So you're saying in the first instance it looks a little bit like s over s squared plus omega squared, and it also looks a little bit perhaps like omega over s squared plus omega squared, but maybe the s's have been shifted. So maybe rather than s over s squared plus omega squared, the s's are shifted. Now I won't repeat for this. I've got about 4 minutes left in the video. I'm going to have to go relatively quickly. So this is where you know you need to complete the square. Okay, so let's do it. Now I'm going to do this fairly quickly. So we want to write s squared plus 4s plus 13. You want to be able to write this as s plus a. So it's basically s squared plus omega squared, but with the s shifted to something. So you want to find the a in the omega such that you can do this. So what you should do is you multiply out the right hand side carefully. You'll get s squared plus 2as plus a squared plus omega squared. Now what you do is, okay, they both have an s squared, that's good. Now compare the s's. So you got 4 s's over here, 2a s's over here, so what's a going to be? And then you have a constant of 13 over here and a squared plus omega squared over here. So what are we going to do? Well, we're going to say that 2a must equal 4. And dividing both sides by 2, you get that a must equal 2. And then what you do is you say a squared plus omega squared must equal 13. The a we've already found is 2, so this is 4 plus omega squared is equal to 13. Take away the 4 from both sides. Omega squared is equal to 9. We do the square root of both sides. Omega is equal to the square root of 9. Now, because this is a little quadratic equation, we know it has two solutions. So it's actually plus or minus the square root of 9, because minus square root of 9 by minus square root of 9 would be plus square root of 9 squared, which is what you want. You can actually choose either, but trust me, just take the positive one. And you end up with 3. So we know that we can rewrite the bottom of g of s as s plus 2 all squared plus 3 squared. And we'll do that on the next page. So what we have is, actually we're going to write that down the bottom of the previous page. So g of s, the thing we're hoping to send back, is 4s plus 8, and the bottom is s plus 2 squared plus 3 squared. Okay, so what and we're going to do this on the next page. It's tempting to split this up as 4s divided by this plus 8 divided by this, but we've seen that might give us problems. So this is very difficult as well. So really what you want to do is actually the 4 is the problem. So take out the 4 and something nice happens there. If you take out the 4, well, 4 by s gives you 4s, and then 4 by 2 gives you 8. And that's going to be good, as we'll see in a second. So if you take out the, if you take out the 4, g of s is equal to 4 times, now I have s plus 2 over s plus 2 squared plus 3 squared. And this is brilliant because if you just forget about this plus 2 shifting for a moment, this is 4 times cos 3t, but it's shifted. So it's actually easier than the last completing the square example. So this is, so the language you could write that, well, in your head as such, write down, this is a shifted 4 cos 3t. And the first shift theorem says bring it back as normal and then multiply by the exponential shift. So we go back to g of t is equal to, fix the 4, and then it says, okay, bring it back as normal. So without the plus 2's, that's just cos 3t. And then multiply by the exponential shift. So it's e to the minus at, where the shifting is s plus a. So the a here is 2, so it's times e to the minus 2t. What type of damping is this? If you want, pause the video and think. So this is, because it's got oscillations, it's a door slamming or oscillating, it's underdamped. So this is everything that you need to do the final step, the medium difficulty step. Where are we going? To do this bit. We have everything. So now what we're going to concentrate is in the full question and looking at the first 3 steps. Thank you.